So what about more coins? What about more qubits? So far or more shots, right? We only looked at measuring the one qubit one time, and that's what we found out so far. If you've ever done experiments, you know you never measure things once. You must measure multiple times. So effectively what we're going to look at now is tossing a bunch of coins up in the air or doing a bunch of qubit measurements and looking at what the statistics will boil down to. So now, instead of taking one shot, one measurement, we're going to repeat the experiment where we prepare some initial state. Here I'll denote it by rho, but think of it as a wave function. That goes into a measurement apparatus. We get a classical outcome that's either 0 or 1, and we label that as a random variable, x1. But then we'll repeat this again. We prepare the state again, we measure, we get an outcome, prepare the state again, measure, get an outcome, etc., etc., etc. And we do this up to capital M times. Notice that we now have a bunch of random variables, x1 through xm. And this one here we'll want to label as capital M, which will denote the total number of shots. And we also have, as we have seen from the previous slide, the idea that each of these is distributed according to this Bernoulli distribution, where the probability to measure an outcome x is determined by the expectation value of this measurement operator. And each and every one of these shots in random variables are totally disconnected and independent. As we like to say, they're IID, independently and identically distributed. So effectively there's a little barrier between them, so they don't talk to each other, there's no correlations among them, etc. So what is then the way to estimate the mean or the probability that the qubit is in the one state? Well, we can define the empirical mean of the random variables in the following way. We'll call it S. Oops. Seem to have zoomed in. Okay, there we go. Where we'll call it S. And let's get our laser pointer up here. S, which is defined as the average over all the random outcomes we measured. Now, try to pause this video if you're a little more sophisticated with your statistics and find the mean and variance of this random variable. You can use some of these properties that we've already derived, such as that the expectation value of any of these observables, they're all the same, just like we did on the previous section for a single qubit, and they all just equal the probability that the qubit is in the one state. And also that the variance is, and this is again a small typo here, that the variance is p times 1 minus p for any of the variables. And finally, it's probably going to be useful to you to try to use the idea that the expectation value is a linear functional, and so you can just distribute across like this. So pause the video, try this yourself, see how far you get. Okay. Let's take a look at what happened here. So the expectation value of S, we just substitute in. Because the E is a linear functional, we just move it through all the way to X. Notice that we dropped the index M because, well, they're all identical and independent, so we can just totally forget about the fact that they're different. And as we showed, you know, this sum here just reduces away, and so we just get the expectation value of X, which then tells us, as we saw from the last section, that this is just the quantum expectation value of this measurement operator M, or just P. In other words, if we average, we get an unbiased estimator of the probability for the qubit to be in the one state. Great. Okay, how about the variance? How noisy is our estimate? You know, does it help to average more, and how much? Well, let's work it out. I'm going to use this identity here, which you can pause the video and try to work out yourself. But essentially the variance of an observable multiplied by some constant a is going to be the variance of that classical random variable times a squared. Because remember, the variance is quadratic if you go back to the definition. So that's where the square comes from. And otherwise, because each of these variables is not correlated in any way, they're independent, we can just break it up into separate pieces. And so you can show that the variance of S looks like this. You substitute in, you have to square the division here because of this expression, and you sum over the variances. Notice that that will reduce into, let's switch to our laser, that will reduce into the variance of a single shot, V of x, divided by m. And so the variance of taking m shots is going to be reduced compared to the variance of one shot by a factor of m. In other words, this is a very famous, standard, and important result. The standard deviation drops as 1 over the square root of the number of shots. So it's better to take more shots. And here's a picture or an animation that tells us how we converge as a function of how many shots we take. So imagine that we take no shots and the probability of our coin is 1/2. Well, effectively, we just haven't done anything yet. But let's play this movie and see what happens as we take more and more shots. You see that there'll be more values along the possible mean. If we only take one shot, we can either have 0 or 1. If we take 2 shots, well, we can now have 0 or 1, or we can have 1/2, or, well, actually, let's see. Let's play this video. So let's see if we have the mouse here. And okay, so you see, if you take 2 shots, you have 3 possible values. You have 0, 1, and 1/2, because you could have had 0, 0, 0, 1, 1, 0, or 1, 1 as the possible outcomes. And if you average those, there's 3 values you can get. And as we go on, you notice how there are more and more possible values that you could have had, but increasingly the probability distribution over these values is going to converge and get narrower and narrower. The center of it isn't moving. That's the expectation value, that's the mean. But the width of it is reducing, and not particularly fast. That's the standard deviation. And it's going as 1 over the square root of the number of shots we took. And so this is very important when you do experiments. You really want to make sure you've taken enough shots so that the error or the width of this curve is pretty narrow, so you have a very good estimate of what the true mean is or what the true value is. Otherwise, you're just somewhere within the width of this curve. Now, in practical quantum computing, this becomes very important to know how accurate your estimate is, for instance, of the energy of a ground state. And there's many methods to prove more rigorously what the confidence interval is, how accurate your result is, how many shots you have to take. We won't go into it. I'll just let you know that there's a nice summary here of all of these inequalities and tools in the bag that get used, oftentimes called tail bounds and tail inequalities, as you might see these in the literature. So if it's handy, take a look at that. Let's come back to our question of understanding the experiment we ran in the beginning. If we now add in projection noise for a finite number of shots, here it's 800, it means that each time we measured, we didn't exactly we only got a 0 or a 1. We took 800 shots, we averaged. Because of the projection noise, the mean is varying. It's, each time we ran the experiment, we'll get a slightly different answer. And we don't exactly get the perfect ideal expectation value of the quantum system. We get these fluctuations around the mean, which dress our results. And so that's exactly where a lot of these fluctuations you see in the experimental data come from. So that brings me to the questions for this piece. So try to pause the chat and see what projection noise is due to, and how do you reduce projection noise? You can't undo it. Do you apply readout error mitigation, or do you increase the number of samples? So pause the video, type in the chat what the answer is. Okay, and I hope you're back with us. So projection noise is due to, the answer is C. And to reduce projection noise, you have to increase the number of samples. If you want more advanced questions and you want to challenge yourself further, I can suggest the following 3 for you to try. And with that, you might be asking, well, that's nice, that's 1 qubit. How about a quantum computer with many qubits? So let's just briefly introduce the core notions you need to be familiar with when you want to extend from 1 to many qubits, where you might have some complicated unitary you're running across, and then you're really interested in observing at the end the outcomes of many qubits in parallel at one time. So here we'll just give you a brief introduction to this idea and what you need to know, but the details we'll get to later. Now, instead of at one time getting 1 bit, you actually get n bits for n qubits. And so we can order all of those n bits and call that one classical random variable, but now it has n bits itself. And oftentimes we'll write it in this form, where the binary string, such as these shown here, might be 0, 0, 0, 0, 1, 0. But this time it's not a sequence of different measurements that we did one after another of the same state. This all came from one run of the quantum computer. What you'll see in practice when you use the quantum computers is that sometimes the bits are ordered from left to right, other times they're ordered from right to left, depending on what you mean by the first bit being in 1 or 0. Is that qubit 0 or qubit n? So keep in mind that there's 2 conventions. The Qiskit convention is, and hopefully I've labeled it right here, so you may want to double check that. But it's the one that has the first qubit all the way to the right. So in this case, the variables belong to this kind of Z2n space, which we've written out here. And you notice that a bit string you can write also as an integer. So another way to write out what these bit strings are, and you'll see this a lot in practice, is that oftentimes people will just write them as integers. And Qiskit allows you to do that as integers or hexadecimals and so on. Again, keep in mind there are different conventions here, but I'd like to just let you know that this is how you go between the 2. So that's where it's important to know that these different integers can correspond to different bits. But at the end of the day, what you always want to calculate are generally expectation values. And we saw that for 1 qubit, the expectation value of the Z operator was just P0 minus P1, the probability of 0 minus 1. We also showed that the sum of the 2 probabilities must be 1. It's a resolution of the identity. Once you have 2 qubits, you have probabilities over 4 bit strings, 0, 0, 0, 1, 1, 0, and 1, 1. And here I've written out for your convenience, and I challenge you to try this yourself, to show that the 4 Pauli expectation values in the Z bases for 2 qubits can be written in terms of the probabilities of the bit strings like this. Now, if that looks suggestive, and you might wonder, how do I generalize that to even more qubits? Since oftentimes in chemistry and other applications, we're interested in the expectation value of some observable, and we need to understand how to compute that. You can take all of these expectation values of the Paulis that you're interested in calculating, and you can write them as a vector. You can do the same with the probabilities. Notice that there's an equal number of, there's 2 to the n of each. And if this picture here looks suggestive, you recognize immediately that in effect what we've done is we've taken a vector of probabilities transformed it by some linear map or matrix into a vector of Pauli expectation values. And in fact, the Pauli expectation values are just transformed by this vector by this matrix W from the probabilities. That allows you to also go backwards. Sometimes you want to go from Pauli's back into expectation, into probabilities. If you're wondering about the structure of this matrix and it looks familiar, we won't go into it here, but I'll just point out for those who want to take a detour on a slightly more advanced but very fundamental piece of quantum physics, that this transformation is inherent to quantum. In fact, it's a Fourier transform. In fact, it's known as a Walsh-Hadamard transform. That's a particular type of Fourier transform over binary numbers. It's related to inner products over these spaces. If you are interested in diving deeper and understanding these subtleties that will show up a lot if you go deeper into quantum, take a look at this. All right, folks, let's get to state preparation and measurement error, cutely referred to as SPAM. So, measurements we've understood at the level of an ideal device. But what if evil Eve comes along and slaps the output of our quantum meter, the 0 or 1 classical channel, and injects noise into it? Let's try to understand what such an imperfect device would actually look like. Here we see Eve has come in. The ideal outcome that we've studied so far should have been encoded in a classical random variable called x. But Eve comes along, breaks the wire, whoosh, injects a bunch of noise. So the output we get is y, not x. Imagine the following kind of setup. Ideally, the value that came in was 0 or 1 at x. However, before that, we've calculated how to find the probability of having x0 and x1. However, instead of getting that value directly, we instead get Eve, who comes in and says, well, you know what, with some probability epsilon, I'm not going to give you 0 when you had 0, I'm going to flip the bit and give you 1. So I'm going to introduce confusion, and when the bit was 1, with some probability nu, instead of giving you 1, I'm going to flip the bit and give you 0. So these red arrows denote the confusion as well as the crossing across. In the ideal world, epsilon would be 0 and nu would be 0, and we'd have perfect communication across the channel. But this channel is corrupted by Eve. And so there's only two possible values still to get, 0 or 1, so we could still describe that by some kind of probability vector of y being either 0 or 1. However, that's not the quantum piece we learned earlier. Instead, that probability is now transformed by what we'll call the A matrix that relates the probability of flipping the bit when x is 1 and when y is 0 or 1. And we can summarize the picture above in this kind of matrix. So see if you understand exactly why it's like this. Now, putting these vectors together, we can write down that the probability of getting a noisy output is equal to the transformed ideal probabilities that is transformed through this matrix. And in fact, this is sort of the core result of this section, and the rest is going to be understanding the consequences of it. You can, by the way, notice, and you'll see this in later mitigation sections, that the way to find the ideal outcome is to invert this relationship by using the A inverse matrix. But let's not jump ahead too much yet. But maybe it's a little bit of my excitement about how understanding noise can lead us to overcome noise. But Nick will cover that in the next lecture. In the ideal case, this A matrix should be purely diagonal in the identity. It doesn't do anything. In the non-ideal case, let's first understand what the properties of this A matrix are. And what is the probability of finding the value y to be in the state 1, given the probability vector of x? So pause the video, challenge yourself, and come back. Okay, I hope you gave it a good shot. Let's take a quick peek. Well, you notice that the columns sum to 1. 1 minus epsilon plus epsilon is 1. Nu plus 1 minus nu is 1. So each column of this matrix has a sum of 1. And we understand that as it's called a stochastic matrix, just to introduce a little bit of nomenclature. We won't use that term again. And we'll notice that that's a consequence of the normalization of the probability, right? If x comes in as 0, it has to get distributed to either 0 or 1. We can't have it go elsewhere. Now let's look at the probability of y. We can introduce these two notations for the probability of x and y. The probability of y has to be the probability of y being 1 given that x was 0, so this is the conditional probability, times the probability that x was 0, and likewise the way that we could have obtained 1 for y is by having x be in 1 with some probability of x being in 1. And so if you work this out, the probability of y is this expression here. Let's visually examine it. So here you see the ideal probability to measure our outcome x. This is determined by the quantum state. And here's the noisy probability to measure y on the y-axis. In the ideal case, we would just have a straight line between the two, shown by this blue curve. They're perfectly one-to-one correlated, no problem. However, what the noise does, as you see, is that it's going to tilt the line and shrink it a little bit. And meaning that you notice in this expression, we have first the offset over here. Even at an ideal probability of 0 for x, the probability of y is not 0. And you notice up on the top right corner, even if x is supposed to be deterministically 1, because of the imperfect apparatus, we still get some mixed probability for y. So notice how already the contrast of the curve is reduced. In fact, it's this reduction in contrast that's very important, because imagine in the worst case scenario that the red curve was flat. So its slope and offset are determined by these two coefficients. But imagine it was perfectly flat. Well then, for any probability of x, we'd get the same probability of y. In other words, there's no way to tell anything out of the quantum system. It just looks like total garbage. So that's the worst case, that we could have. In fact, that's this kind of contrast, how close to perfect we are, or how much this red curve deviates from its lowest to highest value, is known as the assignment fidelity. And this is a measure you'll see reported for the real quantum devices. The assignment fidelity tells you about how close to great your quantum measurement is. In the worst case, the fidelity is going to be 0. That's essentially the contrast that you see here. In the best case, it's 1. So let's take that back into our noisy curve, and let's take a look at what happens in real life. Well, if we have these two measurement errors, you'll notice it's a little hard to see, but there's a slight shift here of the 0 line. Now, our curve is biased. It's not exactly centered as it was before, but it's slightly shifted off. It's a little tricky to tell. On top of that, notice how there's a reduction in the contrast overall. You know, the curve never reaches plus or minus 1, which we observed in the very initial case. And that all has to do, especially at the value 0 here, this is precisely given by epsilon, and sort of the total contrast of the curve, or in a sense our signal, is dictated by our fidelity, f of a, of the assignment fidelity. Good. So now we can see how an imperfect measurement apparatus is going to shrink and offset our signal. Try these following questions to see if you can tackle these, and type them in the chat. Let everybody here know what we think the right answers are. Is readout error due to measurement apparatus, classical limitation, or core of quantum physics? And in order to reduce the error bias, what can you do? So pause the video, try this yourself. Okay, let's come back to it. So readout error is due to, it's not really the core nature of quantum physics, that's projection noise. It is generally due to a measurement apparatus that could be made more efficient, which has to do with classical limitations, but it's not a fundamental classical limitation. For question 2, to reduce the readout bias, increasing the number of samples won't help. It's not that you can't undo it, as we will see soon, but you can apply readout error mitigation, which is a technique that will be introduced in the following lecture. That's his whole point, and that's like applying this inverse A matrix. So then that brings us to state preparation. We've seen what an imperfect measurement apparatus is like. What about an imperfect initial state? Imagine that we wanted to prepare the state 0. Eve comes along, slaps our quantum wire, adds noise to it, and instead we get some mixture of things. In fact, imagine the following model of the noise of what Eve does. Eve has a box, and out of the box, instead of the quantum state we wanted, Eve is just randomly going to throw out either 0 or 1 with some probability p to obtain the state 1. And we have no idea which of the two states she's given us. And then we can run our quantum algorithm, but it's on an unknown initial quantum state. The way to describe the situation in the quantum setting is to say that we can use density matrices, and here we're going to introduce them in an operational sense, just to say, let's take our pure state psi, write it as an operator like this with the bracket notation that we've used several times now. So now this is a 2x2 matrix for the qubit. In particular, for the 0, 0 state, of course, this is 1, 0, 0, 0, and for the 1, 1 state, this is 0, 0, 0, 1. And then we must weigh each of them by a probability of obtaining that state 0 or that state 1 from Eve. And so I can write these out in the following way, down here, mixing the two. Oops, there we go. And now let's take that exploration and see what it will look like. Okay, let's take a look. By the way, notice that it looks like this whole thing that Eve is doing looks like applying a random X gate. That's just a footnote for what will come next. So we can work this out. Recall what we showed earlier in the lecture in terms of what the matrix representation of these dyads looks like. And so you can show that 0, 0 is this matrix, 1, 1 is this matrix. Here I've worked it out for you explicitly, so that the final density matrix or density operator of this state looks like this. Okay, it's diagonal, it has 1 minus p and p on the diagonal. And let's see why this is a good representation to use in order to calculate the outcomes of our quantum mixed system. Now, in order to understand what the expectation value of an operator A is for a pure state, we typically look at the overlap between, or rather the expectation value, the bra operator ket notation like this. We sandwich the operator between the pure state and its dual. For a mixed state, all we have to do is to do the same operation on each individual realization, which looks like that. But now we must weigh it by the probability of having had that realization. In other words, Eve took out of the box 0, we did our algorithm, we got a value. Or Eve took out a state 1, gave it to us, we did our algorithm, we got a different value. And we must weigh each of those outcomes or trajectories by the probability of having had that particular initial state. And so the way to write that out is like this, with the weights 1 minus p and the weight p. And I'll introduce a bit of notation here, which you may have seen before, known as the trace. So this is, we can show, is equivalent to taking the trace of the product of our quantum state rho and this quantum operator A that we're interested in taking the expectation value of. If you want to recall what the trace of a matrix is, for a matrix like this that's 3 by 3, the trace of A is just the sum of the diagonals. So just keep that in mind. It's the sum of the diagonals. Try to work this out for the expectation value of the Z operator, or observable. So imagine that A hat is Z hat, the poly Z. So here's what the expectation value of Z looks like. We would want to take the trace, there we go. We want to take the trace of the Z expectation value like this, where we take the trace of Z multiplied by rho, which is going to be equivalent, as we saw on the previous page, of taking the expectation value of each realization of having either Eve given as 0 or having Eve given as 1, weighted by their respective probabilities. And we see that the expectation value of Z is 1 minus 2 times the probability of getting the 1 state instead of the 0 state, as we ideally would have seen. Now, you can show that, and pause the page and try this yourself, or pause the screen and try this yourself. You can show that similarly for the X observable and the Y observable. For our initial quantum state here, the block vector is 0, component is 0, so block vector component X is 0, Y is 0, and of course the trace of the identity is always 1. And that's sort of the normalization of the probability, which is equivalent to saying that the trace of rho is 1. These are the general property of the density matrix. And there's another way to look at how close to an ideal pure state without any error our density matrix rho is, and that's to look at the trace of rho squared, known as the purity, which, and hopefully I got the lower bound right here, but should ideally go between 0 and 1. Good. So try this yourself. Well, first, if you haven't paused the video, try it now, but let's get into it. So for our density matrix that looks like this, with the basis vectors written in this form, we can also equivalently write it from, if you remember from earlier pictures, as 1/2 the identity plus 0 times the X poly, 0 times the Y poly, those components are 0, plus 1 minus 2p times the Z component. This is one way to decompose it. And more generally, you can show that for any mixed qubit state, you can always write down the qubit density matrix as a decomposition over the 4 polys, weighted by the expectation value of each poly, where the expectation value of X here is the expectation value with respect to this state. So, and that will be a very, very useful trick to keep in mind and have moving forward. The effect then of Eve flipping the qubit randomly is to shrink the length of the block vector. In this case, starting in the +1 state, or the 0 ground state here, as Eve increases the probability of doing something bad to our quantum state and flipping it to 1, we'll see that the length of the block vector shrinks at a rate of 2 times the probability, since the block vector can go from -1 to +1 instead of 0 to 1 like the probability. Another measure of how bad Eve has affected our quantum state is to look at the purity of the state. Here is the trace of rho squared, which, if you try to show this yourself, you will see is just 1/2 1 plus the length of the block vector. So in fact, on the previous slide, it should have gone from 1/2 to 1. And so here we can see that for our case, the purity of our quantum state, how far away it is from the surface of the Bloch sphere, from being ideal, is reduced by this 1 minus 2p squared. Now the purity is a useful measure because when we go to multiple qubits, we'll be able to calculate this rather more easily and look at the overall decay. So we'll do that in just a second. Let's first set up the scenario for what happens when you have not one qubit, but n qubits in your quantum processor. And you're really interested in the preparation of just the 0000 state, but in the presence of Eve, flipping independently and individually each of the qubits with some probability p. We won't work it out here. This is a little bit trickier, a little harder, but try to see if you can do the derivation yourself. You can write out the density matrix as a tensor product of the individual quantum system density matrices, the ones we just analyzed on the previous page, where p is the individual qubit probability to be in the one state. Sometimes we call that the thermal occupation or probability. What is very interesting to note is that if you then calculate the purity of that n qubit quantum state, which remember is just a tensor product of the individual ones, you see that as a function of the probability of Eve doing something bad, and as a function of the number of qubits that you have, you get this exponential decay of how close to an ideal quantum state you are. Ideally, the purity should be 1 if there was no error in state preparation. But as you add qubits, you have more and more possible errors in each time you run your experiment. And you get these exponential decays that really begin to penalize you pretty quickly once you even have a 1, 2, or let alone 5% state preparation error. By the time you have 50 qubits, you're almost in a very mixed state. So keep that in mind next time you run your quantum calculation or talk to your friendly experimentalist. Tell them to make sure their preparation of the quantum state is going into the ground state. So let's jump into perhaps the most exciting part for me, which is incoherent noise. And this is going to look at, in our final chapter, a journey into real quantum circuits that aren't miscalibrated. It's not an error that happens at the classical device. It's not a coherent error. This is a whole new class of error. This is when we think about the fact that our quantum system is not an isolated object, but is in fact connected to the environment. It's connected to other quantum systems. We call it an open quantum system. And in this chapter, we'll do as many of the calculations together. I'll try to give you the flavor as well as some of the results. They're a little bit more challenging, but I want to give you a look at how to understand what happens in this open quantum system dynamics. And this is going to launch you into a whole new world of quantum trajectories, open quantum systems, error mitigation, and a whole new fun discipline. So let's jump right into it. Starting with a toy model example where you have a qubit starting in the ground state. You want to do some unitary, but Eve comes along and shoots a very mean set of noise at our unitary. Let's model that noise as the injection of a random gate that Eve isn't going to tell us what to do. Each time we apply U, inseparably Eve penalizes us with some random gate. Back to our favorite example, imagine that with probability 1 minus p, that's the identity, and with probability p, that's the bit flip gate, our favorite gate. So what happens? How do we analyze and understand this? By the way, this is called the quantum trajectory unraveling. So there are two cases. We call it trajectory A, where with probability 1 minus p, Eve applies the identity. She doesn't really do anything in that case. Or in trajectory B, with probability p, Eve is going to flip our qubit from 0 to 1 and vice versa. Now in this algorithm, we'll take the time steps, time 0, time 1, time 2, and progress from left to right. Now, as we saw in the spam section, there are two different purely unitary trajectories in both cases, but we don't know which one happened. In this case, it's not because of the initial state, it's because of the unitary that was applied. And so like in the last section, we'll see that this will result in a mixed state. To understand how the noise will act here, let's write this out for trajectory A explicitly. This is a purely unitary trajectory, but I'll write it out in terms of density matrices so that we get familiar with this notation and how we add them up. So we start in the 0, 0 state. After time step 1, Eve has applied the identity gate, which you can write in this case on the left and on the right, where this is the conjugate transpose or dagger on the right, because remember the bra is the conjugate transpose. And finally, Eve applies the unitary. Of course, I and I dagger are the same thing, and I times 0 is 0. But I'll write it out in this way so that it's easier to see what's going on. In trajectory B, we have the exact same situation. The only difference is that Eve applies x instead of I in the middle. So how do we describe the average quantum evolution in this case? Well, this is where you can use our ideas from earlier, that at time step t, we simply have two possibilities of having one density matrix or the other. We weigh them by their respective probabilities. Notice that that allows us to combine the second two rows and understand the way to write the operation of Eve in which we, without our knowledge, Eve applies one of these gates, but it's indiscriminate. We don't know which one it is. So the way to write that is that it looks like the density matrix on average is transformed by having either applied the identity gate with probability 1 minus p, or having applied the bit flip gate with probability p. And this is our first introduction to a quantum channel, or a quantum noise map, that takes one density matrix into another. And Eve is, of course, symbolized here in this lambda channel. If you're a little more advanced and you'd like to challenge yourself, pause the video and try to work out the effect of this noise on the Bloch's vector of the qubit. Recalling that for a general qubit state, we can always write it like this, with x, y, and z being some real numbers. Calculate the expectation values before we apply the noise channel, and calculate them right after we apply the noise channel, and see what you get. What is the effect of the noise on the Bloch vector? Now, if you wanted to do that, you can use all of these tricks here to show, and this is going to give you a few tricks to use, but we'll focus on the main result in a section. For those that want to get more technical, it's useful to remember that any Pauli to any integer power n is itself when n is even, and it's the identity when n is odd, and is the identity when n is even. The trace of any Pauli is 0. You can show that easily with the matrices, except for the identity. So in fact, maybe I should say or equals 2 for A being the identity. Good. And the trace of any two Paulis is 2, only if they're themselves, otherwise it's 0. And the trace has these properties. So if you wanted to write this out, you can show that the expectation value of the identity kind of worked out through this is the trace of the identity times rho. Of course, the identity leaves rho alone. The trace you can distribute across because it's a linear functional. You can pull out all of these coefficients x, y, and z outside the trace. And the trace of x, y, and z are 0, so only the identity term contributes. So, of course, that's 1. You can similarly do this for the x expectation value. Again, distributing x across the term. You can quickly see that anytime x multiplies anything other than x, that term will be 0. The only time you get x, a term surviving, is when x multiplies itself, because that's the only time you get the identity, and all other Paulis are traceless. So there's only one term you care about, and of course you get the expectation value of x being x for the initial state. So if you work this out and through, you will see that initially the qubit started in a Bloch vector x, y, z, and after the noise channel, the Bloch vector was impacted in having its y component and its z component reduced by some factor of 1 minus 2p for the y and z terms. In other words, our bit flip noise doesn't affect the trace of the fidelity of the density matrix, doesn't affect the x component. In fact, x commutes with x, so you can see where that comes from. But anytime the Eve is going to flip our qubit with the x gate, she's going to introduce a loss of information in the y and z components that is going to be proportional to this factor 1 minus 2p. That factor is oftentimes called the Pauli fidelity, as it tells us how much the block vector is going to shrink in that particular direction, y or z. So this is the effect of incoherent noise at a first pass, is to begin to shrink your block vector. It doesn't have to be in all directions, it doesn't have to be the same, but it's going to reduce it. Okay, let's take a step back from the equations and let's visualize it. In the ideal world, before any noise, our pure states live on the surface of the Bloch sphere, as you can show for any pure normalized wave function. They form the surface of the Bloch sphere. After the noise is applied, let's say without any special gauge, just the identity, you notice that overall the possible states, the pure states that came in, shown by this darker grayed curve, have shrunk in the y and z directions. So the surface has contracted, the purity is reduced, and we understand that as a loss of information. In other words, we don't know what Eve did. Because we don't know what Eve did, we have less information about the state, and our block vector has shrunk correspondingly. In this case, this is all the same except for the x direction, which is unaffected. So noise doesn't have to always destroy everything. You might ask, how does this relate to our experimental example where we apply the noise again and again and again? And here, we won't work out the details. We'll try to keep it at the high-level message, but I challenge you to try yourself to see what happens if you take the noise channel and you apply it again and again and again to a general block vector. You can see that each time you apply the noise channel, you're going to get this reduction of the block vector components of y and z, as we showed in the earlier piece. So try to use these results from earlier to, within a line or two, show what will happen. Okay? And if you wanted to try that, I hope you pause the video. Otherwise, we'll jump right ahead into showing that the effect of repeating the noise again and again, or applying the gate, a noisy gate many times with incoherent noise, is going to yield this kind of exponential decay of your block vector components. So notice how the identity and x are unaffected. However, the y and z components are going to decay exponentially with the depth of the circuit D at a rate given by the fidelity of the noise in that direction. And the fidelity is just 1 minus 2 times the probability of an error. And so the damping factor for any depth circuit here in the x direction is 1, but in the y and z directions is going to be here plotted for a fidelity of 0.95, is going to decay pretty quickly. So how does that compare to the coherent noise repeated d times that we saw earlier? If you remember the discussion, we said that the coherent noise has this quadratic worst case error growth. If we expand our expected value for z in terms of noise to lowest order, you notice that now this is linear in the depth and in our error. So to first order, the incoherent noise is penalizing us in a linear rather than quadratic fashion. And so in that sense, incoherent noise is a little bit easier to deal with, or a little less penalizing at first. So now I'm excited because finally we get to put all the pieces together. We now understand incoherent noise. It will give us the overall decay that we saw in our experimental data earlier, sort of here shown with this orange decaying curve. I fitted about a value of 0.008, which is a very small number of probability to bit flip by Eve our qubit at each time step, or each depth. But you notice that it adds up pretty quickly. There's a state preparation error of about 2%. There's a readout error of about 2 and 5%. There's only 800 shots in our experimental data. And finally, there's an over-rotation of about 3 degrees. And this now basically perfectly fits our experimental data. We can really understand all of the pieces coming together, from the projection noise that we saw, from the spam that is going to shrink the contrast and give us some more of this variance, from the coherent error that tells us about the oscillations, to now the incoherent error that tells us about the decay. At this stage, you might wonder, is that the only kind of incoherent quantum noise there is? We won't get into it in this particular lecture, but I'd like to just point out that Eve didn't just have to apply the identity and X gate. Eve could have chosen a whole family of different gates to randomly apply with different probabilities, such as I and Z, or perhaps I, X, Y, and Z, and maybe they're with equal probabilities or different probabilities. And each of these different noise channels will act on the qubit sphere in different ways, but ultimately the story is always the same. You get shrinkage of the Bloch sphere, you get a contraction, you lose information, the purity reduces. So for those of you who really want to push yourself, I challenge you to try to go back to what we just did for the bit flip noise and basically do it again for the phase, depolarizing, and stochastic Pauli noises, and work out the effect of each of those on the Bloch vector components, and you'll see that it's pretty similar. For those who want to challenge themselves even more, you can look at amplitude damping, which is related to something we call T1. But again, this is harder, this is extra credit. Okay, folks, great work. We have covered now 5 or 6 chapters from coherent noise, measurement, spam, and incoherent noise. And we've really come to the final section of our lecture, which is, how do you get rid of noise? Well, what's the outlook? How about larger experiments, real devices? Really, the question we have to ask ourselves is, can we take what we've learned here and generalize it? Is it really possible to understand and overcome quantum noise with accuracy, efficiency, and scalability, the things we need, on a real quantum device? You know, one of these big quantum devices that has all kinds of imperfections, that has all kinds of incoherent, coherent, and other noise processes. Energy relaxation, dephasing, coherent crosstalk, classical crosstalk, quantum crosstalk, state preparation, measurement errors, control errors, photon shot noise, 1/f charge. There's all many types of different things that can go wrong. But almost all of these can be summarized or abstracted in the way that we've shown you so far and end up looking like bit flip, phase flip, channels, measurement errors, and so on. Now, you might ask, great, we can understand those at some level, as I'd like to claim, but how do we then deal with them? And very broadly, to give you a course overview, there are 3 ways. Either you monitor the error, an error occurs, you detect the error, and then hopefully you can recover from it in some way. You can undo the error if you know exactly what it is. If you knew Eve flipped your qubit, you can just unflip it. And this is known as quantum error correction. However, this is very challenging and tricky because monitoring these systems in practice in real time, detecting these errors, decoding them, undoing them, is very tricky and difficult, and it's where the field is going and headed, but is not really the state of things today. The second thing you can do, and this is very new and exploratory, is to monitor the system in real time, anticipate the error from occurring, anticipate that an error will occur, before it ever has a chance to occur. So there's a very different, much more complicated type of monitoring. And then there's a telltale signal that can tell you before an error even occurs and has the chance to propagate. And this is called catching and reversing quantum jumps. But this is, while shown in a real experiment by myself and colleagues recently, it's still too far out of reach to scale to large quantum devices, since it's very challenging. So where we are today is that we don't monitor the system actively. An error does occur, and it goes unnoticed, undetected. But not all hope is lost, because we can still undo the error despite that. And that's really what the next lecture will tell you about. So I'll simply set the stage here by differentiating for you error mitigation, which is the strategy before quantum error correction, that really says you work with what you have. The benefit is you can suppress errors on classical results. You can get better, more noise-free expectation values. There's usually no extra quantum overhead you need. You don't need extra qubits like you do in quantum error correction. However, you need to run usually the experiments for longer. There's still a trade-off. There's still a no free lunch theorem. If you want lower error, you have to pay some price, and usually it's that you need to run your experiments for longer than you normally would have. It's a method that is very efficient and practical today, and we use it in all of my experiments, and most people use it at this point. But it's limited in its long-term applicability because it scales poorly when you go to very large and deep circuits. That doesn't mean it won't be useful even when we have quantum error correction. It just means it's not the end of the story. And the next really big step is quantum error correction, which in principle can suppress any error to an arbitrary level. It requires a very large qubit overhead, which is what makes it challenging today, and potentially the classical cost isn't easy either, but it allows you to, in principle, overcome noise fully. On the state of where things are today, there isn't just one way to undo and try to cancel the noise. As we've seen, there's many kinds of noise, and in fact there's many kinds of error mitigation techniques, as Nick will cover in the next lecture. There's ones that are fast and easy, but usually not as good for everything, and there are ones that are very accurate. They know and use a lot of the information about the noise of the quantum device, but oftentimes they're slower. So there's a whole landscape of these techniques, which is why it's important to understand the noise and the techniques if you want to get the most out of your quantum device. This is a very evolving and exciting space. I've given you all the basics to launch your career and journey, to use some of the tools, to use Qiskit. And if you want to really keep track and know what is the latest and best and greatest in quantum computing today, thanks to our team here, we host every Friday at noon Eastern Time this Qiskit seminar series on YouTube, where you can meet and interact in real time with some of the world's leading experts. We've had over 120 seminars with probably 140 years of watch time and more so far. So if you want to continue your journey at a more advanced level and really keep up to date with where the field is headed, feel free to tune in and stay in touch with us there. So folks, that really brings us to the end of today's journey. We've covered all of these types of noise. We've taken an outlook at how you can use the knowledge to undo the noise. There's some bonus content as well as the lecture material PDF that we'll share along with this lecture. I want to thank you for being such great students, making it through this long and deep journey. I hope you're proud of yourself. We have covered a lot. We started very basic and got very far. And I want to leave you with this quote, one of my favorite quotes from Albert Einstein. I will let you read it. But the main thing is not to stop questioning, to keep on that journey. And even if every day you learn just one new thing, if you get one new thing out of this lecture, then it was worth it. So with that, you will have your lab work. You will have the notes that go along with these. I will see you in the Q&A session. Check out the problems and references I've given throughout this lecture. Maybe go back to those dangerous bends when you can. Stay in touch, have fun, and thank you for being such great sports today. Until we meet again, thank you.